Something is off about the light, not the kind of off you fix with calibration, not a small shift in brightness, not a rounding error in a dataset. A telescope sitting 1,000,000 miles from Earth has captured photons that should not be reaching us like this from when they are coming. Light from a time we thought was still buried in darkness. Light from an era that, according to our best models, had not yet learned how to shine. And yet, it's there, clear, structured, measurable, as if the universe turned on earlier than it was supposed to. Tonight, we are going to follow that light backward, from the moment it touched the mirror of the most advanced telescope ever built, all the way back to a point in cosmic history that may not behave the way we expected, because what James Webb has just seen is not just distant, it is misteamed. If you enjoy deep space stories built on real science, subscribe. What comes next is one of the most unsettling windows into the early universe we have ever opened. Take a moment, because once we step into this, the timeline of everything begins to feel less certain. For most of human history, light was simple. You looked up at the night sky, and what you saw felt immediate. Stars, fixed in place, a quiet dome above the Earth. It took centuries to understand that every point of light is a message traveling through time. The moon is 1 second away. The sun is 8 minutes. The nearest star beyond that, over 4 years. By the time you reach distant galaxies, you are not seeing where they are. You are seeing when they were. Astronomy is not just looking far, it is looking back. And for a long time, there was a boundary to how far back we could go. Not because the universe ended, but because our tools did. Older telescopes could see billions of years into the past. Enough to watch galaxies mature, enough to understand structure. But the earliest chapters of cosmic history remained hidden. Not dark in the sense of empty, dark in the sense of unreachable. Because the deeper you look, the more the universe stretches the light itself. As space expands, it pulls on the wavelengths of light traveling through it, stretching them, slowing their frequency, shifting them toward red and beyond red, into infrared. The older the light, the more stretched it becomes. And eventually, it slips completely out of the range of what human eyes and traditional telescopes can detect. So for decades, scientists had a gap, a missing chapter, the period when the first stars ignited, when the first galaxies began assembling, when the universe transitioned from darkness to light. We built models to fill that gap. We simulated what should have happened. Small, faint structures forming slowly, stars igniting in scattered pockets, a gradual rise from simplicity to complexity. It was a careful timeline, built on physics, tested against everything we could observe, and for a while it held. Then James Webb opened its mirror, and the light it captured did not follow that script. Before we go deeper into what Webb saw, you need to understand what kind of machine it actually is. Because this is not just a better telescope, it is a different kind of eye. Webb does not look for visible light the way earlier instruments did. It is tuned for infrared, for heat, for the stretched, ancient glow of photons that have been traveling for more than 13 billion years. Its mirror spans over 6 meters, made of 18 hexagonal segments coated in gold. Not for appearance, but because gold reflects infrared light with extreme efficiency. Behind it sits a sun shield the size of a tennis court. 5 layers, each designed to block heat from the sun, earth, and moon. Because, to detect faint infrared signals, the telescope itself must be colder than almost anything in space. Any warmth would drown the signal, so Webb operates in deep shadow, at a gravitational balance point called L2, where it can stare into the universe without interference. From there, it does something no telescope before it could do. It looks into time ranges that were previously invisible, and it does it with enough sensitivity to resolve structure. Not just smudges, not just hints, actual shapes, actual galaxies, actual light from the first few 100 million years after the Big Bang. That was the goal, to confirm what we thought we knew about the early universe, to finally see those first faint steps towards structure. But the moment the first deep images came in, something felt wrong. Not dramatically at first, just enough to make people pause. The light Webb was capturing from deep time looked too developed, too organized, too bright, as if the universe had skipped steps. And then came something even stranger, because it was not just what the objects looked like, it was when they appeared. To understand why that matters, you need to understand what it means for light to come from a specific point in cosmic history. When astronomers talk about distance, they are really talking about time. A galaxy seen 13 billion light years away is not just far. It is being seen as it existed 13 billion years ago. So when Webb detects light at extreme distances, it is effectively opening a window into a very specific era of the universe, an era that has a defined place in the timeline. Right after the Big Bang, the universe was too hot for atoms to exist. Then it cooled enough for hydrogen to form, but there were no stars yet, no galaxies, just a dark, expanding sea of gas. This period is often called the Cosmic Dark Ages. Eventually, gravity began to pull that gas together. The first stars ignited. Their radiation began to change the surrounding space, breaking apart neutral hydrogen, making the universe transparent to light. This transition is known as reionization. It marks the moment the universe became visible in the way we understand it. And according to our models, this process took time, hundreds of millions of years. It was not instant. So if you look far enough back, you expect to see darkness, or, at most, extremely faint, early structures just beginning to form. That is the expectation. That is the timeline. Now imagine pointing the most powerful infrared telescope ever built into that era, and seeing light that suggests something already exists there. Not barely, but clearly. That is what Webb has done. It has captured light from a point in cosmic history where we expected the universe to still be in transition. And that light is not weak. It carries structure. It carries information. It carries a level of organization that suggests something had already formed. And that creates a problem, because it means one of two things must be true. Either the timeline is wrong, or something in the early universe happened faster than we thought possible. Neither option is small. To understand this tension, we need to talk about how astronomers actually measure when something is happening in the universe. Because we are not just guessing distances, we are reading them from the light itself. This is where redshift comes in. When light travels through expanding space, its wavelength stretches. The more distant the source, the more space has expanded during its journey, and the more stretched the light becomes. Astronomers measure this stretching as redshift. A higher redshift means the light has been traveling longer, which means it comes from earlier in cosmic history. It is like a timestamp encoded directly into the light. Webb is extremely good at measuring this. It can take the faint glow of a distant object and break it into a spectrum, reading how much the light has shifted and determining when it was emitted. So when Webb detects light at a very high redshift, it is not just seeing something far away, it is seeing something very early. And that is where things become difficult to ignore, because some of the light Webb is capturing corresponds to times when the universe was only a few 100 million years old, a fraction of its current age. And yet, that light does not look like it is coming from a universe that young. It looks like it is coming from something that has already evolved, already formed, already structured, as if the universe accelerated its own development, and then left us to figure out how. But this is only the beginning of the problem, because once you accept that the light itself is real, you have to ask what produced it. And that question leads into one of the most important tensions in modern cosmology. What exactly was shining that early, and how did it get there so fast? What exactly was shining that early, and how did it get there so fast? Because light does not exist on its own. It has a source. And when you trace that source back into the early universe, you begin to run into a timing problem that does not resolve cleanly. The first sources of light in the universe were stars. Not small, quiet stars like our Sunday. The first generation was different. Massive, short-lived, burning hotter and brighter than anything that came after. These are often called population 3 stars. They formed out of almost pure hydrogen and helium, no heavy elements, no prior generations. They were the first attempt at structure, and they changed everything. Their radiation began to break apart the neutral hydrogen around them. Their explosions seeded the universe with heavier elements. Their deaths paved the way for the next generation of stars. But even these stars needed time to form. Gravity had to pull gas together. Density had to increase. Collapse had to begin. Nothing about that process is instant. Even under ideal conditions, it unfolds over millions of years. And that is just for stars. Galaxies are something else entirely. A galaxy is not just a collection of stars. It is a system, a gravitational structure. Gas flows in, stars form, stars die, black holes grow, matter organizes, rotation emerges. That takes time, not millions, hundreds of millions, and often billions of years. So when Webb captures light from a time when the universe is still in its early stages, you expect to see hints of this process. Small clusters, irregular shapes, chaotic formation. What you do not expect to see is anything that looks settled, anything that looks mature, anything that suggests the system has already had time to evolve. But some of the light Webb is capturing does exactly that. And that is where the discomfort begins. Because now, the question is no longer just about light. It is about structure. The light coming from these early points in cosmic history is not random. It is not diffuse. In some cases, it is concentrated, organized, as if it is being produced by systems that already know how to exist. And that leads to a deeper question. What if the universe did not wait as long as we thought to begin building complexity? To explore that, we need to zoom out, way out, and look at the universe not as individual objects, but as a timeline. The Big Bang marks the beginning, not an explosion in space, but an expansion of space itself. Everything moving outward, cooling, spreading. At first, the universe is simple. Hot plasma, particles, radiation. No atoms, no structure. Then comes recombination, when the universe cools enough for electrons to combine with protons, forming neutral hydrogen. At this point, the universe becomes transparent. Light can travel freely. This is when the cosmic microwave background is released, a faint glow that still fills the universe today. After that, darkness. No stars yet, no galaxies, just gas, slowly collapsing under gravity. This is the period we call the Dark Ages. Then, at some point, the first stars ignite, light returns, reionization begins, and the universe transitions into the structured cosmos we recognize. That is the sequence. That is the expected order. But what Webb is seeing suggests that somewhere in that sequence, things may have overlapped, or accelerated, or unfolded differently, because the light it captures seems to belong to a stage that should come later. Not by a small margin, by enough to matter. And this is where redshift becomes more than just a measurement. It becomes a challenge, because if the redshift is correct, then the timing is correct. And if the timing is correct, then the universe produced structured light earlier than expected. And if that is true, then something about the early conditions must have allowed for faster development. So what could do that? There are a few possibilities, none of them simple. One idea is that star formation in the early universe was far more efficient than we thought. In the modern universe, when gas collapses to form stars, a lot of that gas gets pushed away. Radiation pressure, stellar winds, feedback processes that limit how quickly stars can form. But in the early universe, those feedback mechanisms may not have been as strong, or may not have existed yet in the same way, which means gas could collapse more completely, more quickly, forming stars at a higher rate. That could explain brighter light, earlier light, more structure, but it raises new questions, because even if stars form faster, galaxies still need time to organize. Another idea is that what we are seeing is not just starlight, but something else, something more intense. Black holes. In the centers of galaxies, black holes grow by pulling in matter. As that matter spirals inward, it heats up, releasing enormous amounts of energy, sometimes outshining the entire galaxy. If black holes in the early universe were growing rapidly, they could produce bright signals earlier than expected. But again, that requires time. Black holes do not appear fully grown. They start small, they accrete, they evolve. So, if they are already contributing significant light at these early times, they must have formed quickly, or started larger than expected. And that leads to a third possibility, that the seeds of structure in the early universe were not as small as we thought, that the initial density fluctuations, the tiny differences in matter distribution after the Big Bang, were larger or behaved differently, allowing gravity to act faster, pulling matter together more efficiently, accelerating the entire process of formation. But this begins to push against the foundations of cosmology, because those initial conditions are not arbitrary. They are measured from the cosmic microwave background, from the distribution of matter, from decades of observation. Changing them is not a small adjustment. It is a shift in the starting point of everything. And yet, the light Webb is capturing is quietly forcing that conversation, because it exists, and it does not match expectations cleanly. But there is another layer to this, one that makes the situation even more complex, because we are assuming that the light is telling us exactly what we think it is, that its brightness reflects its source, that its structure reflects reality. But in the universe, light does not always travel untouched. Between the source and us, there is everything: galaxies, dark matter, clusters, filaments, mass that bends space. And when space bends, light bends with it. This is gravitational lensing, a phenomenon predicted by general relativity and confirmed again and again. When light passes near a massive object, its path curves, sometimes slightly, sometimes dramatically. It can be magnified, distorted, even split into multiple images, which means that what we see is not always a direct image of the source. It is an image filtered through the structure of the universe itself. And when you are looking at light that has traveled for over 13 billion years, it has passed through a lot. So there is a possibility that some of the light Webb is detecting appears brighter than it truly is, amplified by gravitational lensing along the way. That could make distant objects seem more developed than they are, more massive, more structured. But lensing has limits. It cannot create structure that is not there. It can enhance, distort, reveal, but not invent. And the consistency of what Webb is seeing suggests that lensing alone cannot explain everything. So we are left with a situation where multiple explanations exist, but none fully resolve the tension. And the deeper you go into the data, the more it feels like the early universe was not as simple as we thought, not as slow, not as gradual, but something more dynamic, more efficient, more willing to build structure early. And that brings us back to the light itself, because beyond brightness, beyond structure, there is something else encoded in it, something even more fundamental: the fact that it exists at all. Because there was a time in cosmic history when light could not travel freely. Before reionization, the universe was filled with neutral hydrogen, and that hydrogen absorbs certain wavelengths of light, especially ultraviolet light from young stars. So even if stars existed, their light would not travel far. It would be trapped, scattered, absorbed. The universe would remain opaque until enough radiation built up to ionize that hydrogen, clearing the fog, allowing light to move. This is a threshold, a transition point, and according to our models, it happens over time, not instantly. So when Webb detects light from before or during that transition, it is not just about when stars formed. It is about when the universe became transparent. And if that transparency is appearing earlier than expected, then the timing of reionization may need to be reconsidered, which, again, loops back into the same core tension. The early universe may have evolved faster than we thought, but how much faster? And what allowed that acceleration? Because this is not just about adjusting a timeline, It is about understanding the rules that govern the first few 100 million years of existence, the period that set the stage for everything that followed. And right now, those rules are being questioned, quietly, carefully, but persistently, because the light is there, and it is not behaving the way we expected. And the more Webb looks, the more of it appears, and the more of it appears, the harder it becomes to treat it as an anomaly, because one unexpected signal can be noise, two can be coincidence, but a pattern is something else, and that is what is beginning to emerge. Webb is not just detecting isolated flashes from deep time, it is building a catalogue, a growing list of objects whose light comes from an era that should still be uncertain, yet appears strangely confident, bright, defined, present, as if the universe crossed a threshold earlier than expected. To understand why that matters, you have to step back and look at how cosmology builds its expectations in the first place. Because the timeline we keep referencing was not guessed, it was calculated, simulated, refined over decades. At the center of that timeline is something called the Standard Model of Cosmology, a framework that describes how the universe evolved from its earliest moments to now. It includes the expansion of space, the role of dark matter, the influence of dark energy, the formation of structure, the growth of galaxies, and for years it worked remarkably well. It explained the cosmic microwave background, it matched the distribution of galaxies, it predicted large-scale structure, it held together across multiple independent observations, which is why what Webb is seeing is not just interesting, it is disruptive, because the model does not easily produce what Webb is detecting at those times, not without stretching assumptions, not without adjusting parameters, and sometimes not at all. This is where the phrase "unexpected point in cosmic history" becomes more than just a title, because it is not just that the light is distant, it is that it seems to belong to a stage that, according to the model, should not yet look like this. It is as if you opened a history book, turned to the early chapters, and found cities already built, not foundations, not village, cities with structure, with organization, with signs of development that imply time has already passed. That is the feeling, and it forces a question that cosmology does not answer lightly. Did the universe build faster than we thought? Or are we misunderstanding what we are seeing? Because there is always a second possibility, that the interpretation is incomplete, that the light is telling us something, but not exactly what we think. For example, brightness. When we see a bright object at great distance, we often interpret that as meaning it contains many stars, a large galaxy, a mature system, but brightness can come from other processes, active black holes, dense starbursts, extreme conditions that produce more light per unit mass. So, one possibility is that these early objects are not large, but efficient, small systems producing disproportionate amounts of light. That could shift the interpretation, make them appear more developed than they are. But even that has limits, because efficiency does not remove the need for structure, and structure still takes time. Another possibility lies in the nature of the early universe itself. Conditions then were not the same as now. Higher densities, different radiation environments, less metal content, all of which could influence how matter behaves, how gas collapses, how stars form, how light is produced. It is possible that under those conditions, the universe was capable of organizing itself more quickly, that the early rules allowed for faster pathways to complexity. But this raises a deeper question. If the rules were different then, what does that say about the consistency of physics across time? Are the laws of physics fixed, or do they behave differently under extreme conditions? This is not a comfortable question, because much of cosmology relies on the assumption that the same rules apply everywhere, at all times. Change that, and the entire framework becomes more fluid, less predictable. But the tension does not stop there, because the light Webb is capturing is not just about when things formed, it is also about how they are arranged. And that leads us into something even larger, the structure of the universe itself. If you zoom out far enough, the universe is not random. It is not just scattered points of light. It has a pattern, a structure that repeats across scales, filaments, clusters, voids, a vast interconnected network known as the cosmic web. Galaxies are not evenly distributed. They gather along these filaments, like beads on threads, and between those threads, there are enormous empty regions. This structure did not appear instantly. It grew, over time, guided by gravity, shaped by dark matter, refined by expansion. So when Webb looks into the early universe, we expect to see the beginnings of that web. Faint outlines, loose groupings, nothing fully formed. But some observations suggest that even this structure may have started organizing earlier than expected. Not fully developed, but recognizable, aligned, coherent, and that adds another layer to the problem. Because now, it is not just individual objects forming early, it is the large-scale pattern itself, which suggests that the underlying scaffolding of the universe may have been established sooner, or more efficiently, or under different conditions. And that brings us to dark matter, the invisible component that makes up most of the universe's mass. We cannot see it, but we can see its effects. It pulls, it shapes, it holds structures together. Without it, galaxies would not form the way they do. The cosmic web would not exist. Everything would be more diffuse, less organized. So if structure is appearing earlier than expected, one possibility is that dark matter behaved differently in the early universe. Perhaps it clumped faster, or flowed differently, or interacted in ways we do not yet fully understand. There are theories, warm dark matter, wave-like models, alternatives to the standard cold dark matter assumption, each with different implications for how structure forms. And Webb's observations are beginning to provide data that can test those ideas. But again, nothing resolves cleanly. Each explanation solves part of the problem and introduces another, and that is the pattern. Every answer opens a new question. Every explanation leads to another layer, and the deeper you go, the more it feels like the early universe was not just a simpler version of today. It was something qualitatively different, something that may not follow the same intuitive progression. And this brings us back to the light, because ultimately, everything we are discussing comes from photons, tiny packets of energy, traveling across billions of years, carrying information, not just about where they came from, but about the conditions that produced them, their wavelengths, their intensity, their distribution. All of it encodes history, and Webb is reading that history with unprecedented clarity, which means that if there is something unusual about the early universe, we are now in a position to detect it, not as speculation, but as data. And that is where the real tension lies, because the data is starting to point in a direction that does not fully align with expectation. And when that happens in science, it usually means one of two things. Either the data is incomplete, or the model is, and right now, both possibilities are still on the table. But there is another dimension to this, one that is less about physics and more about perspective. Because when we talk about seeing light from an unexpected point in cosmic history, we are also talking about the limits of observation, what we can see, what we cannot, and how those limits shape our understanding. There is a boundary to the observable universe, not a wall in space, but a horizon in time, a limit defined by how long light has had to travel. Beyond that horizon, there may be more universe, almost certainly is, but we cannot see it. And as we look deeper, we approach that boundary. We get closer to the earliest moments we can observe, closer to the edge of what is knowable through light. Webb is pushing right up against that limit, seeing light from times that were previously inaccessible. And what it is finding there is not a simple, quiet beginning. It is active, structured, already in motion. And that raises a final, unsettling possibility. That what we thought was the beginning of visible structure may not be the true beginning at all. that the processes that built the first stars and galaxies may have started earlier than we can currently see, hidden in a period we still cannot observe directly, before the universe became transparent, before light could travel freely, a phase of development that left its imprint but not its direct signal. If that is true, then Webb is not just showing us something unexpected. It is showing us the edge of a deeper story, one that begins before the light itself. And that is where the mystery expands. Because now we are not just asking, what produced this light? We are asking, what happened before it? What happened before it? That question sits at the edge of everything we can observe. Because light is not just information, it is a boundary, a limit. There is a point in cosmic history where the universe becomes visible, and before that, it does not. No stars, no galaxies, no photons traveling freely across space, just darkness filled with matter slowly organizing itself. And yet, what Webb is seeing suggests that by the time the universe becomes visible, something had already been set in motion, something that allowed structure to appear quickly, almost immediately after the fog cleared, which raises the possibility that the real beginning of complexity is hidden in a time we cannot directly observe, a time before light could travel, a time where the rules of formation may have been very different. To understand how serious that possibility is, you need to think about how fragile our timeline actually is. We often talk about the age of the universe as if it is fixed, about 13.8 billion years, a number derived from the expansion rate, from the cosmic microwave background, from models that have been tested over decades. But that number depends on assumptions. Assumptions about how fast the universe expanded, how matter behaved, how energy evolved over time. If any of those assumptions shift, even slightly, the timeline shifts with them, and Webb is beginning to press on exactly those assumptions, because the light it captures does not just challenge structure, it touches expansion itself. The deeper you look into the universe, the more you rely on understanding how space has stretched over time. Because distance is not static, the universe is expanding, galaxies are moving away from each other, and the rate of that expansion determines how we interpret what we see. This rate is called the Hubble constant. It tells us how fast space is growing, and for years, scientists have measured it in two different ways. One method looks at the early universe, using the cosmic microwave background, reading patterns from when the universe was only a few 100,000 years old. From that, they calculate what the expansion rate should be today. The second method looks at the nearby universe, using stars and supernovae as markers, measuring distances directly, building what is known as the cosmic distance ladder. Both methods are precise. Both are based on strong physics, and they should agree, but they don't. The numbers are close, but consistently different, not by chance, not by error, by enough to matter. This is known as the Hubble tension, and for years, scientists hoped it would go away, that better measurements would bring the numbers together. But as instruments improved, the gap remained, and then Webb entered the picture. With the ability to observe stars in distant galaxies with unprecedented clarity, it began to check the distance ladder, to verify whether the nearby measurements were accurate, and what it found was that they were, which means the tension is real. The universe is expanding at a rate that does not match what we expect from the early universe, and that matters here, because expansion affects everything. It determines how light travels, how distances are measured, how time is interpreted. If the expansion history is not exactly what we thought, then the timeline of cosmic history shifts, and that could help explain why Webb is seeing light from an era that feels out of place. Because maybe that era is not where we thought it was. Maybe the universe reached certain milestones earlier, or faster, or under different conditions. But again, this is not a clean solution, because changing expansion introduces new problems. It affects age, it affects structure, it affects the entire framework, and yet, it is one of the few ways to reconcile what we are seeing. Another possibility is more subtle, that the laws governing the early universe included components we do not fully understand, forms of energy that existed briefly and then disappeared, influencing expansion, influencing structure formation, leaving behind effects, but no direct trace. Some scientists refer to this as early dark energy, a temporary contribution to the energy of the universe that could have accelerated expansion at specific times. If something like that existed, it could shift the timeline, compress events, allow structure to form earlier than expected. But this idea is still under debate. It fits some observations, conflicts with others, and like many explanations in this area, it solves part of the puzzle while leaving the rest open, because that is the nature of this problem. It is not one anomaly, it is a cluster of tensions, all pointing in a similar direction. The early universe may not behave exactly the way we modeled it, and Webb is not just hinting at that, it is showing it. But there is another layer to this, one that sits beneath everything else, and it has to do with how we interpret what we see at all, because every observation we make of the distant universe is filtered not just by distance, but by everything in between. Light does not travel through empty space. It travels through a universe filled with matter, visible and invisible, and that matter bends space, which bends light. Gravitational lensing is not rare, it is constant. Every photon that reaches us has been influenced, to some degree, by the structure it passed through. Sometimes the effect is small, sometimes it is dramatic, but it is always present, which means that when Webb looks deep into the universe, it is not seeing a perfect image, it is seeing a projection, a version of reality shaped by billions of years of gravitational influence. For most purposes, this distortion can be accounted for, modeled, corrected, but at extreme distances and extreme times, those corrections become more complex, more uncertain, and it raises a quiet question. What if part of what we are seeing is influenced in ways we do not fully understand yet? Not false, not imaginary, but altered, enough to shift interpretation, enough to make something appear more developed, or more distant, or more structured than it truly is. This is not the leading explanation, but it is part of the uncertainty, and it reminds us of something important. We are not observing the universe directly. We are observing light that has traveled through it, and that distinction matters, because it means our map of the cosmos is always a reconstruction, built from signals, interpreted through models, and those models are now being tested in ways they have never been tested before, which brings us back to the core idea. James Webb has captured light from an unexpected point in cosmic history, not just far, not just old, but mistimed, and the more we analyze that light, the more it suggests that our understanding of the early universe may be incomplete, not wrong in a simple sense, but missing pieces, missing processes, missing dynamics that shaped how quickly structure emerged. And when that happens in science, it does not mean everything collapses. It means we are at the edge of a transition, a moment where new data is pushing against established theory, where the next step is not refinement, but expansion, a broader framework, a deeper model, something that can account for what we are now able to see. Because for the first time, we are not just theorizing about the earliest visible universe, we are observing it directly, and it is not as quiet or as simple as we thought. It is active, layered, already building complexity at a pace that challenges expectation, and that realization carries a kind of weight, because it means that the story of the universe is still being written, not in the past, but now. With every new observation, every new dataset, every new piece of light that reaches us after billions of years. And Webb is not finished. It is still looking, still collecting, still pushing deeper, which means that whatever we think we understand right now may only be the beginning. Because if light from that early can already challenge our models, then what happens when we see even further? What happens when the next layer comes into view? What happens when the next layer comes into view? That question is no longer hypothetical, because Webb is not just peeking into the early universe once. It is building depth, layer by layer, each observation stacking onto the last, each dataset refining what we thought we understood, and quietly shifting it. And as that depth increases, something else becomes clear. The early universe is not just brighter than expected. It is more crowded, more active, more populated with sources of light than models predicted, which introduces another tension. Not just how fast structure formed, but how much of it formed. Because when you look at a deep field image from Webb, you are not just seeing a few distant objects. You are seeing thousands, each one a galaxy, each one a system, each one a story, and many of those stories begin earlier than they should. This is where the idea of number density comes in. How many galaxies exist at a given time in cosmic history? According to the standard model, the earliest epochs should contain fewer galaxies, because there has been less time for them to form, less time for matter to collapse, less time for stars to ignite. But Webb is finding more than expected. Not dramatically in every case, but consistently enough to matter, and that consistency builds pressure. Because now, it is not just a few outliers. It is a pattern across populations, which suggests that whatever process is driving early structure is not rare, it is widespread. And that changes how you think about the early universe entirely. It stops being a slow, cautious beginning, and starts looking more like a rapid transition, as if once conditions were right, structure emerged quickly and broadly. But what determines those conditions? That question leads into one of the most important phases in cosmic history, reionization. This is the period when the first light sources began to transform the universe, when radiation from early stars and galaxies started to ionize the surrounding hydrogen, turning the universe from opaque to transparent. It is not just a milestone, it is a gateway. Before reionization, light struggles to travel. After it, the universe opens up. And the timing of that transition is critical, because it determines when we can begin to see clearly. And Webb is now probing that boundary in detail, detecting light from objects that sit right at the edge of reionization, and possibly even within it, which raises an important question. Did reionization happen earlier than we thought? Or did it happen faster? Or was it driven by sources more powerful than we expected? Because the brightness and number of early objects suggest that something was generating significant radiation, enough to clear the fog sooner, enough to allow light to travel further. And if that is true, then the first generations of stars and galaxies were not just present, they were influential. They were shaping the universe on large scales, earlier than expected. But again, this leads to another layer of complexity, because reionization is not just about light. It is about energy, and energy in the early universe interacts with everything. Gas temperatures, star formation rates, black hole growth, all of it is connected. So, if reionization shifts, the entire early timeline shifts with it. And that brings us to something even more fundamental, the relationship between matter and energy in the early universe. Because everything we have discussed so far, structure, light, galaxies, depends on how matter behaves under gravity and how energy influences that behavior. And at the center of that relationship is something we still do not fully understand, dark matter, and something even more mysterious, dark energy. Dark matter shapes structure. It pulls matter together, forms the scaffolding, creates the potential wells where galaxies can form. Dark energy does the opposite. It drives expansion, pushes space apart, acts on the largest scales, and the balance between these two determines how the universe evolves. But in the early universe, that balance may not have been the same as it is now. Dark energy, in particular, is assumed to be constant, a steady influence. But what if it wasn't? What if its strength changed over time? What if it behaved differently in the first few 100 million years? That could alter expansion, alter density, alter how quickly matter clumps together, and that could help explain why Webb is seeing structure earlier than expected. But this idea comes with consequences, because changing dark energy means changing the fundamental dynamics of the universe. It is not a small tweak. It is a shift in the core framework, and yet, it is one of the possibilities being explored, because the data is pushing us there, and that is something worth pausing on, because in science, it is rare for observations to push so directly against foundational assumptions. Most of the time, new data fits within existing models or requires only small adjustments, but every so often, you reach a point where the model itself begins to strain, where the edges do not align, where the explanation feels forced, and that is when a field begins to change. Not all at once, not dramatically, but gradually, as new ideas are tested, new frameworks are proposed, new ways of thinking are explored, and that is where cosmology may be right now, not in crisis, but in transition, because the universe we are observing is slightly different from the one we expected, and that difference is growing more precise, more detailed, more difficult to ignore. But there is still another layer to this story, one that goes beyond structure, beyond timing, beyond even physics, and it has to do with limits, because no matter how powerful our instruments become, there are boundaries we cannot cross. Not technological, but fundamental. There is a point beyond which light has not had time to reach us, a horizon defined by the age of the universe. Beyond that horizon, there may be more galaxies, more structure, more history, but we will never see it, because the light from those regions has not arrived, and may never arrive. Due to the expansion of space, Webb is pushing as close to that horizon as any instrument ever has, capturing light from just a few 100 million years after the beginning. But even Webb cannot see into the earliest moments. The true beginning remains hidden, not because it is gone, but because its light is inaccessible. And that means there is always a gap, a region of cosmic history that we cannot directly observe, only infer, only model, only imagine, and that gap is exactly where many of these questions originate, because if something unusual happened there, we would not see it directly. We would see its consequences, encoded in the light that comes after, and that is exactly what Webb may be detecting, not the event itself, but its imprint, a signal that something in the early universe behaved differently, left a trace, accelerated development, shifted timelines, and now, billions of years later, that trace is arriving as light, and we are trying to interpret it, trying to understand what it means, and that process is still unfolding, because every new observation adds detail, but also adds complexity. It narrows some possibilities, expands others, and keeps the central question open. Why does the early universe look more developed than expected? Why is the light coming from that era so clear, so structured, so present? And perhaps most importantly, what does that say about everything that came before? What does that say about everything that came before? Because once you accept that the early universe may not follow the timeline we expected, you are no longer just adjusting a model. You are reopening the origin story, not the beginning itself, but the way the beginning unfolds into structure. Because everything we see today, every galaxy, every star, every planet, is the result of processes that started in those first few 100 million years. If that phase behaves differently, then everything downstream is affected, and Webb is giving us our first clear look at that phase, not as theory, but as observation, which is why the tension feels different this time, because it is not coming from simulation. It is coming from light, real photons, measured, analyzed, confirmed, and they are telling us that something about the early universe is more complex than we thought. But to understand just how deep that complexity might go, we need to step even further back, closer to the beginning, closer to the conditions that set everything in motion. Right after the Big Bang, the universe was not just hot, it was extreme, densities beyond anything we experience now. temperatures so high that particles behave differently. For a brief period, the fundamental forces of nature may have been unified, not separate, not distinct. Then, as the universe expanded and cooled, those forces separated. Gravity, electromagnetism, the strong and weak nuclear forces, each taking on its own role. This transition defined how matter would behave, how particles would interact, how structure would eventually form. But we do not fully understand those earliest moments. Our equations begin to break down. Our models rely on extrapolation. We know what happened after a certain point, but not exactly what happened at the very beginning. And that leaves room for processes that we have not yet accounted for, processes that could influence everything that came later, including how quickly structure formed. One of the most important ideas in this context is inflation, a period of extremely rapid expansion in the earliest fraction of a second, faster than anything that came after. Inflation explains several key features of the universe: why it appears flat, why it is uniform on large scales, why small fluctuations exist that later grow into galaxies. But inflation is still a theory, well supported, but not directly observed, and its details matter, because those tiny fluctuations it produces, the seeds of structure, determine how matter clumps together over time. If those fluctuations were slightly different, larger, more uneven, then gravity would have more to work with. Structure would form faster, earlier, more efficiently, which could help explain what Webb is seeing. But, again, this is not a simple adjustment, because the fluctuations we observe today in the cosmic microwave background are measured with incredible precision. They match inflation models remarkably well, so changing them is not trivial. It requires careful consideration, new physics, new mechanisms, and yet the possibility remains. Because the early universe is not fully constrained, there is still room for variation, still room for dynamics we have not yet fully understood. And that brings us to something even more subtle, the idea that the universe may not be perfectly uniform. We often assume that on large scales, the universe looks the same everywhere, no preferred direction, no special location. This is called the cosmological principle, and it has been a foundational assumption in cosmology, supported by observations of the cosmic microwave background, supported by large-scale galaxy surveys. But there are hints, small ones, that the universe may not be perfectly uniform. Large structures that seem too big, regions that behave slightly differently, patterns that challenge statistical expectations. Nothing definitive, nothing that breaks the model completely, but enough to raise questions. And Webb is now extending those observations into earlier times, looking to see whether those patterns persist, whether the early universe was as smooth as we think, or whether there were variations that influenced how structure formed. Because if the universe was not perfectly uniform, then some regions could evolve faster, form structure earlier, produce light sooner, which would explain why we are seeing signals from unexpected points in cosmic history. But again, this is not a confirmed conclusion. It is a possibility, one of many, and that is what makes this moment in cosmology so interesting, because there is no single explanation, no clear answer, only a set of observations that collectively point towards something missing, something incomplete. And that brings us back to the role of James Webb itself, because Webb is not just a telescope, it is a threshold, a transition point in our ability to observe the universe. Before Webb, the early universe was mostly theoretical. We had hints, indirect measurements, simulations. Now, we have direct observation, and that changes everything, because theory can adapt, it can adjust, it can evolve, but observation is fixed. It is what it is, and when observation does not match expectation, the expectation must change. Not immediately, not recklessly, but inevitably, and that process is already underway. Scientists are re-examining models, running new simulations, testing new ideas, looking for ways to reconcile what Webb is seeing with what we thought we understood. and in some cases, finding that reconciliation is not straightforward, which is not a failure, it is progress, because this is how science moves forward, not by confirming what we already believe, but by revealing where those beliefs fall short. And right now, the early universe is revealing something subtle but persist, a signal that the first chapters of cosmic history may not be as simple as we imagined, and that signal is coming from light that has traveled for billions of years, crossed unimaginable distances, passed through countless structures, and arrived at a mirror of gold to tell us a story we are still learning how to read. But there is one more piece to this, one more layer that brings everything together, because when we talk about unexpected light, we are not just talking about timing, we are talking about meaning. What does it mean for the universe to reveal something earlier than expected? What does it mean for structure to appear ahead of schedule? What does it mean for our timeline to feel slightly out of place? It means that the universe is not just larger than we thought, it is more flexible, more dynamic, less constrained by our assumptions, and that realization has consequences, not just for cosmology, but for how we understand our place in it, because every time we push deeper, every time we build a better instrument, every time we capture light from further back in time, we are reminded of something simple. We do not see the universe as it is, we see it as it reveals itself to us, piece by piece, layer by layer, and each layer has the potential to change the picture, not completely, but enough to matter, and Webb is adding a new layer, one that reaches into a part of cosmic history. We have never seen this clearly before, and what it is showing us is not a quiet beginning, but a universe already in motion, already building, already producing light, from a point in time where we expected less. And that is where the story opens, rather than closes, because this is not the end of the mystery. It is the beginning of a deeper one, a question that now sits at the center of modern cosmology. If the universe could produce this kind of light, this early, what else is waiting just beyond our current reach? If the universe could produce this kind of light, this early, what else is waiting just beyond our current reach? Because every time we think we are close to the limit moves, not physically, but conceptually. We believed there was a clean boundary between darkness and light in the early universe, a gradual transition, a predictable unfolding. But Webb is showing something less orderly, less patient, a universe that seems willing to organize itself quickly once the conditions allow it. And that suggests something important, that the early universe may not have been a slow build, but a rapid ignition, a threshold event where once certain conditions were met, structure emerged across multiple scales at once. Stars, galaxies, radiation, all rising together, not perfectly synchronized, but not as staggered as we imagined. And if that is true, then the gap between nothing visible and something structured may be much narrower than we thought, which changes how we think about the beginning of everything we can see, because it means the transition from simplicity to complexity could have been abrupt, not gradual, and that raises a deeper question. What determines that threshold? What flips the universe from dark to active? Because if we understand that, we understand the moment the cosmos became what it is now. One idea is that it is driven purely by density. As the universe expands, matter spreads out, but early on, it is still dense enough for gravity to act efficiently. When certain regions reach a critical density, collapse begins. Stars form, light ignites, but density alone may not be the full story, because the distribution of matter matters just as much as the amount. If matter is clumped in the right way, collapse can happen faster, more efficiently, which brings us back to those initial fluctuations. Tiny variations in density, amplified over time. If those variations were slightly stronger in some regions, those regions would evolve faster, form structure earlier, produce light sooner, and Webb may be detecting exactly those regions, not the average early universe, but the earliest pockets of rapid development, the places where conditions aligned just right, where the universe began building ahead of schedule. If that is the case, then what we are seeing is not a contradiction, but a selection effect. We are seeing the first places where light could emerge, the leading edge of cosmic structure, which means there may still be regions at the same time that remain dark, unseen, because they have not yet crossed that threshold. This would create a patchwork early universe, some areas lit, others still in darkness, a mosaic of development, rather than a uniform transition. And that idea fits with some models of reionization, where ionized bubbles expand outward from early galaxies, gradually merging, filling space, until the entire universe becomes transparent. In that scenario, Webb is not seeing a fully developed early universe. It is seeing the brightest, earliest regions, where the process began first. But even this explanation does not remove all the tension, because the brightness and structure of some observed objects still push beyond what we expect, even in the most optimistic models. And that brings us back to a familiar place, where multiple explanations exist, but none fully close the gap. And that is where the most interesting science happens, because it forces a shift in perspective. Instead of asking which explanation is correct, we begin asking what combination of effects might be at play. Faster star formation, early black hole activity, variations in density, shifts in expansion, differences in dark matter behavior, all interacting, all contributing, all shaping the early universe in ways we are just beginning to understand. And that complexity is not a weakness, it is a signal that the system is richer than our initial models captured, that the early universe is not a simple stage, but a dynamic environment, full of competing processes, feedback loops, threshold effects, an emergent structure, which is exactly what you would expect from something as vast and complex as the cosmos. But there is still something deeper here, something that goes beyond individual explanations, because what Webb is really revealing is not just a faster timeline, it is a different perspective on time itself. When we say something happened too early, we are comparing it to a model, a sequence, an expectation. But the universe does not follow our expectations. It follows its own rules, and those rules may not produce a clean, linear progression. They may produce overlap, acceleration, regions that evolve faster than others, moments where multiple processes converge, creating bursts of complexity, which means that cosmic history may not be as smooth as we imagine. It may be uneven, layered, full of local variations, where some parts of the universe move ahead, while others lag behind. And what we are seeing with Webb may be the earliest example of that, the first visible evidence that the universe does not evolve uniformly, but selectively, based on conditions, based on environment, based on the distribution of matter and energy. And that changes how we interpret everything, because it means that the light we see is not just a snapshot of time, it is a snapshot of conditions, of where the universe was ready to become something more. And that idea leads to one final realization, one that sits quietly beneath all of this. The universe is not just expanding, it is revealing itself, and it does so in layers, not all at once, not evenly, but gradually, as light from deeper and deeper times finally reaches us, each layer adding detail, adding complexity, adding new questions. And right now, we are seeing a layer we have never seen before, a layer where the universe is just beginning to light up, and yet already showing signs of maturity, already hinting at processes that started earlier than we can observe, already challenging the idea that we fully understand the first chapters of cosmic history. And that is where the story becomes something more than science, because it is no longer just about measurements, or models, or data. It is about perspective, about recognizing that even our most advanced tools are still only showing us part of the picture, that beyond what we can see, there is more structure, more history, more processes unfolding in ways we have not yet imagined. and that realization carries a certain kind of weight. Not uncertainty in a negative sense, but openness, the understanding that the universe is not a finished story. It is ongoing, expanding, revealing itself piece by piece, and every time we look deeper, we find something that pushes us further. For centuries, we believed the sky was static. Then we learned it was vast. Then we learned it was evolving. Now, we are learning that even its earliest visible moments may not behave the way we thought. And that is not a failure of understanding. It is the beginning of a deeper one, because the universe has not changed. Our view of it has, and Webb is sharpening that view to a level where even small discrepancies become meaningful, where light from the edge of time can challenge the structure of theory, where a signal from billions of years ago can reshape how we think about the beginning. And somewhere in all of that, in the light that has traveled longer than anything we have ever measured, there is a message. Not a simple one, not a clear answer, but a direction, a hint that the universe is more active, more complex, and more willing to surprise us than we were prepared for, and that the story of its earliest light has only just begun to unfold, and that story is still unfolding. Because what Webb has revealed is not a finished picture. It is a beginning, a glimpse into a layer of cosmic history that was hidden until now. And like every layer before it, it does not close questions. It creates them, because once you see light from an era that feels out of place, you cannot unsee it. You have to follow it. You have to ask where it leads. And that path pulls you deeper into the structure of the universe itself, into the way matter organizes, into the way time is measured, into the way light carries history across unimaginable distances. Because the light Webb captures is not just data, it is evidence of process, of events that happened billions of years ago, under conditions we are still trying to reconstruct. And as more of that light arrives, the picture becomes sharper, but also more complicated, because the early universe is not revealing itself as a simple system. It is revealing itself as layered, interconnected, driven by multiple forces acting at once. Gravity pulling matter together, radiation pushing it apart, dark matter shaping invisible scaffolding, dark energy stretching space, all of it interacting, all of it evolving, and all of it leaving traces in the light we now observe. Which means that understanding this light is not just about identifying sources, it is about decoding a system that may not behave in the linear way we once assumed. And that realization changes the nature of the problem, because it means we are not just adjusting timelines, we are trying to understand a network of processes that unfolded under extreme conditions in a very short span of cosmic time, and that requires new approaches, new models, new ways of thinking. Already, researchers are building simulations that incorporate more complex physics, more detailed interactions, more realistic conditions, trying to reproduce what Webb is seeing. And in some cases, they are getting closer, but not fully there, because the data is still ahead, still pushing, still revealing new details faster than models can absorb them. And that is what makes this moment unique. We are not waiting for better instruments. We already have them. We are waiting for understanding to catch up. And that takes time, but it also takes perspective. Because when we talk about unexpected light, we are also talking about the limits of expectation itself. For decades, cosmology has operated with a framework that works remarkably well. But like any framework, it is built on assumptions, on simplifications, on the best information available at the time. And when new information arrives, those assumptions are tested, not all at once, but gradually, through tension, through inconsistency, through moments where the data does not align cleanly. And that is exactly what is happening now. The early universe is not breaking the model completely, but it is stretching it, testing its edges, forcing it to adapt. And that is how progress happens, not through certainty, but through discrepancy, because discrepancy points to something missing, something not yet understood. And that missing piece is what drives discovery. So what could that piece be? It might be something subtle, a refinement of how star formation works under early conditions, a better understanding of feedback processes, a shift in how we interpret brightness and structure. Or it might be something deeper, a change in how dark matter behaves, a new component of energy in the early universe, a modification of how gravity operates on large scales, or something else entirely, something we have not yet imagined, because that is always a possibility, that the solution is not just an adjustment, but a new idea, a new framework, one that makes the current tensions make sense. But we are not there yet. We are still in the phase of observation, of analysis, of trying to map what we are seeing before we fully understand it. And that is a necessary step, because you cannot explain something until you know what it is. And right now, we are still learning what this early light represents. Is it the first true wave of structure? Is it a set of exceptional regions? Is it evidence of faster processes? Is it a sign of deeper physics? The answer may be all of the above, or something else entirely. But whatever it is real, and it is measurable, and it is not going away, because Webb will keep observing, keep collecting, keep pushing deeper, and as it does, the dataset will grow, the patterns will become clearer, the outliers will either resolve or multiply, and each new observation will refine the picture, slowly, carefully, building toward an understanding that matches what we see. But even when that happens, even when we develop a model that explains this light, the story will not end, because there will always be another layer, another question, another boundary to push against. That is the nature of science, and it is especially true in cosmology, because the universe is not just large, it is deep, not just in space, but in time. Every photon carries a timestamp, every observation is a step backward, and the further back we go, the closer we get to the limits of what we can know. But those limits are not static, they move as our instruments improve, as our understanding grows, and Webb is moving them now, bringing us closer to the earliest visible moments than ever before, and showing us that even there, even at the edge of observable history, the universe is not simple. It is active, complex, already building structure, already producing light, from a point in time where we expected less. And that is the quiet shift, not a dramatic overturning of everything we know, but a subtle realignment, a recognition that the early universe may be more dynamic, more efficient, more layered than we once believed. And that recognition matters, because it changes how we think about origins, not just the origin of galaxies, but the origin of everything that followed. Because if structure begins earlier, then the chain of events that leads to stars, to planets, to life, begins earlier too, and that stretches the story, expands it, makes it richer, more complex, and in a way, more interesting, because it means the universe did not wait. It did not unfold slowly and predictably. It moved, it built, it organized itself as soon as it could. And we are only now beginning to see that through light that has traveled longer than anything we have ever measured. Light that left its source when the universe was still in its earliest chapters, and arrived now to tell us that those chapters may not read the way we expected, that the opening of the cosmic story is not quiet, but active, not simple, but layered, not fully understood, but just beginning to be revealed. And somewhere beyond that light, beyond what Webb can currently see, there are earlier moments, earlier processes, earlier structures forming in ways we cannot yet observe. And one day, with better tools, with deeper understanding, we may reach those moments too. And when we do, the story will shift again, because that is what the universe does. It does not stay within the limits we set for it. It expands beyond them and invites us to follow. And it invites us to follow, not with certainty, but with better questions, because at this point, the mystery is no longer just about a few distant signals. It is about how we interpret the earliest visible chapter of existence, a chapter that, until now, was mostly built from inference. Now it is being observed, and it does not look exactly the way we expected. That alone is enough to shift the direction of an entire field. But there is something deeper happening here, something quieter, because the most important part of Webb's discovery is not just what it found, but where it found it. The timing, the placement of that light within cosmic history, because in cosmology, timing is everything. Every model, every equation, every prediction, all of it depends on when events happen. Shift the timing, and the entire structure of understanding shifts with it. And what Webb is showing us is that some of those events may have occurred earlier, or faster, or under conditions that allowed them to accelerate, which forces a simple but profound question. What sets the pace of the universe? Why does structure form when it does? Why not sooner? Why not later? Because once you see evidence that the pace can change, you have to understand what controls it. One possibility is that the pace is not fixed at all, that it depends on local conditions, density, temperature, distribution of matter, radiation environments, all varying slightly across space, creating regions that evolve at different speeds, some ahead, some behind, which would mean that cosmic history is not a single timeline, but a range of overlapping ones, different parts of the universe moving through stages at different rates. And what Webb is detecting are the earliest of those regions, the ones that crossed into visibility first. That idea changes how you think about early, because early is no longer a single moment. It is a spectrum, a range of conditions, where some areas begin forming structure before others. And that means the universe does not turn on all at once. It lights up gradually, unevenly, with pockets of activity emerging before the rest follows. And that fits with the idea of reionization as a patchwork process. But it also suggests something more, that those early regions may hold information about the most efficient pathways to structure, the fastest routes from simplicity to complexity. And if we can understand those pathways, we can understand what drives the universe to build, because at its core, that is what the universe does. It organizes. It takes simple components and assembles them into increasingly complex systems. Atoms, stars, galaxies, clusters, each layer building on the last, each one requiring time and the right conditions. And Webb is showing us that under certain conditions, that process can happen faster than we expected. But there is still a boundary, a limit we cannot cross, because no matter how powerful Webb is, it cannot see everything. There is still a point in cosmic history where light simply does not reach us. Before the first stars, before the first photons could travel freely, a time that remains hidden. And that hidden time is where many of the answers may lie. Because if something unusual happened there, it would shape everything that followed. It would influence how quickly structure formed, how efficiently matter collapsed, how early light could emerge. But we cannot observe that time directly. We can only infer it from the light that comes after, from the signals that carry its imprint. And that is exactly what Webb is giving us. Not a direct view of the earliest moments, but a reflection of them, encoded in the light we can see, which means that every unexpected signal, every mistimed photon, is a clue, a piece of a puzzle that extends beyond our current horizon. And that is where the sense of scale becomes overwhelming, because the observable universe, everything we can see, is already enormous, tens of billions of light years across, filled with trillions of galaxies, each one containing billions of stars, and all of that is just the part whose light has reached us. Beyond that, there is more space, more history, more structure, forever out of reach. And even within what we can see, we are only now beginning to explore the earliest layers, which means that our understanding is still incomplete, not because we lack intelligence, but because we are limited by observation, by what light can tell us. And light is only part of the story, but it is the part we can measure. the part we can analyze, the part that connects us to events that happened billions of years ago. And that connection is what makes discoveries like this so powerful, because they are not abstract, they are real, they are signals that have traveled across time to reach us. And when those signals do not match expectation, they force us to listen more carefully, to question more deeply, to rethink what we thought we knew. And that process is still unfolding because Webb is not done, not even close. Every observation it makes adds to the dataset, refines the picture, and sometimes complicates it, because the more we see, the more detail emerges, and detail reveals nuance, and nuance reveals gaps, places where our models are too simple, too rigid, too reliant on assumptions that may not hold under extreme conditions. And that is where the future of this field lies, not in confirming what we already believe, but in expanding it, building models that can accommodate complexity, that can explain not just the average behavior of the universe, but its variations, its extremes, its unexpected moments, because those moments are where new physics often hides, not in the obvious, but in the discrepancies, in the places where reality does not align perfectly with theory. And right now, the early universe is offering exactly that, a set of observations that do not fully fit, a signal that something is missing, and an opportunity to discover what that missing piece might be. But even as we search for answers, there is something worth holding on to, something that sits beneath all of this. The fact that we can see this at all, that light from billions of years ago, from a time when the universe was still finding its structure, can travel across space and be captured by a machine built by a species on a small planet, orbiting an ordinary star. That connection between then and now is extraordinary, because it means that the universe is not just distant, it is accessible in a limited way, through light, through observation, through careful interpretation. And that accessibility allows us to ask questions that would have been unimaginable just a few generations ago. Questions about the earliest light, the first structure, the pace of cosmic history. And now, those questions are becoming sharper, more precise, more focused, because we are no longer guessing, we are observing. And what we are observing is a universe that may not follow the timeline we expected, a universe that may build earlier, faster, more efficiently than we thought. And that realization does not close the story, it opens it, because if this light, this unexpected signal from deep time is real, and it is, then it is pointing towards something deeper, something about the nature of the universe itself, something about how it began to organize, something about the processes that shaped everything we see today. And we are only at the beginning of understanding it, because the universe does not reveal itself all at once. It reveals itself in layers, and Webb has just uncovered one of the deepest layers we have ever seen, a layer where light appears earlier than expected, where structure is already emerging, where the timeline feels slightly out of place, and where the answers are still just out of reach.